Let's do some calculus problems about local linearization, also called tangent line approximation. In the first problem, we have a bunch of functions that we want to do this for. Before we do any of these, we should think about the general idea first. We've got some nice smooth function, differentiable, call it y equals f of x, and we have some number a in the domain of f of x. I'm thinking of a as fixed. And we'd like to approximate this function with its tangent line at a. We know the slope of the tangent line is f prime of a, the derivative of f at a, and we also know it goes through the point whose coordinates are a comma f of a. Using that information, we can come up with our local linearization formula. We can call the linear function whose graph is this tangent line L of x, L for linear, and it's going to be f of a plus f prime of a times x minus a. Why? F prime of a is the slope. When you expand this out, it is getting multiplied by x. This is certainly a line here because x is to the first power. That's going to be the slope of the line, and it also goes through the right point. When you replace x with this fixed number a, you get f of a plus f prime of a times a minus a, but that's 0, making this entire term 0, making the output equal f of a. This has got the right slope, and it also goes through the right point. That's the function whose graph is the tangent line approximation to f at this point. Now let's go ahead and use it for these examples. In a, the function is f of x equals ln of 1 plus x. What's a? You don't see an a anywhere. Well, that's this thing right there. Whatever we're saying x is near, that is the value of a. So we need to use that. A is 0 for part A, and we need to find the derivative of f, the derivative of natural log of 1 plus x. Well, we know the derivative of natural log of x is 1 over x. So technically, we need to use the chain rule here. We need to plug in 1 plus x in place of that, and then multiply times the derivative of that, but that is 1. So the derivative of this function is 1 over 1 plus x. A is 0. Looking at this formula right here, we need to find f of 0 and f prime of 0. That's pretty easy. F of 0 is ln of 1 plus 0, which is ln of 1, which is 0. And f prime of 0 is 1 over 1 plus 0, which is 1. So this becomes pretty simple here in this example. L of x is f of a, which is 0, plus f prime of a, which is 1, times x minus a. Remember, a is 0 here. This simplifies to x. The local linearization or tangent line approximation to this function ln of 1 plus x near 0 is this very simple linear function L of x equals x. I didn't explicitly say it in this problem, but you could then say that the natural log of 1 plus x is well approximated by this linear function x when x is close to 0. If you wanted to go ahead and make a graph, ln of 1 plus x is the same as the graph of the ln function, shifted to the left by 1 unit. It's got a vertical asymptote at -1. It looks about like this. And the line y equals x looks about like this. It's the tangent line approximation to the ln of 1 plus x graph near x equals 0. The next function you can see here is f of x equals the square root of 1 plus 3x. Once again, a is 0 because we're saying near x equals 0. That implies that that number is the a. Go ahead and do this one here. F of x equals square root of 1 plus 3x. That's the same as 1 plus 3x to the 1/2 power. A is still 0. We need to find f of 0 and f prime of 0. Let's go ahead and find the derivative first. We'll need the chain rule again. We'll bring down that 1/2, plug in the inside function, subtract 1 from the exponent, and then multiply times the derivative of the inside, which is 3. From these things, we can compute that f of 0 is 1 plus 0 to the 1/2 power, 1 to the 1/2 power, square root of 1, which is 1, and f prime of 0 is 1/2 times 1 to the negative 1/2 power times 3. That's the same as 1 over 1 to the positive 1/2 power. It's still 1. 1/2 times 3 is 3/2. So our local linearization, our tangent line approximation function is L of x equals f of 0, which is 1, plus f prime of 0, which is 3/2, times x minus a That's x minus 0. This simplifies to 1 plus 3 halves x, or if you prefer, 3 halves x plus 1. All right, what's going on here graphically? If you graph this square root function near x equals 0, technically its domain goes to x equals negative 1/3, and so that's going to be negative 1/3 there. And the graph is going to go up. The value at 0 is 1, and the slope at 0 is 3 halves. It looks about like this, and the tangent line approximation at this point looks about like that. That's got a vertical intercept at 1 and a slope of 3 halves. All right, part C. Now the function is 1 over x, and now we're using some other value of a. Near x equals 4, that's going to be the value of a. Right? We can't do this near 0 because this is undefined at 0. So for C, f of x is 1 over x, same as x to the negative 1 power. We need the derivative, f prime of x. You could use the quotient rule, but you also could use the power rule. Is negative x to the negative 2, same as negative 1 over x squared. A, again, is now 4, not 0. So we need to compute f of 4 and f prime of 4. F of 4 is 1/4, or 0.25. F prime of 4 is, plug it in there, negative 1 over 4 squared, negative 1/16. And that is the same as negative 0.0625, if I'm doing my arithmetic in my head correctly. I think I should have done that enough to know for sure. I'm going to confirm just to check. Yep, 0.0625. And then L of x, I'll use the fractions, is f of 4, which is 1/4, plus f prime of 4, which is negative 1/16, times x minus 4. More typically, you'd write this as 1/4 minus 1/16 times x minus 4. You can certainly expand this, write it in slope-intercept form. I'll go ahead and do that. 1/4 minus 1/16 x, and then plus 1/4. Oh, it does simplify pretty nicely to negative 1/16 x, but that doesn't make sense. Did I make a mistake? Oh no, excuse me. 1/2 minus 1/16 x. But to tell you the truth, it's technically more useful to have it in this form, because the idea is that you're going to use this function to approximate f of x when x is near 4. And having the x minus 4 there makes that easy to do, maybe even in your head. Like if x were 4.1, for example, you'd have 4.1 minus 4 is 0.1. 1/16 times 0.1 is, well, take this and move the decimal to the left one spot. You'd have, with the negative sign, negative 0.00625, and then add 0.25 to that. You could do it all in your head. You could use this linear function to approximate this function in your head, to approximate ultimately 1 over 4.1. That's kind of amazing if you think about it. All right, last example here is D. The function is sine of x, and the point x is pi over 6. In other words, that's the value of a again. A is now pi over 6. F of x is sine of x. Its derivative, f prime of x, then therefore is cosine of x. A is pi over 6, so we need to compute f of pi over 6. That's sine of pi over 6. In calculus, you always assume the input is in radians, unless told otherwise. Sine of pi over 6 is 1/2. F prime of pi over 6, you can check that with your calculator, is cosine of pi over 6. These are memorized values. That's square root of 3 over 2. That's approximately 0.866. In exact form, L of x is going to be 1/2 plus square root of 3 over 2 times, in parentheses, x minus pi over 6. And then you could use this linear function to approximate the sine function well near a equals pi over 6. Let me make quick graphs for these last two examples. With the previous example, the 1 over x graph looks about like this. And say this is 4 here. The tangent line approximation looks about like that. That is going to be what this function is. And with the sine function near pi over 6 here, the tangent line approximation is going to look about like this. Okay, so you can double check these things with your calculator too. In problem number 2, we're trying to estimate a value without a calculator, like I hinted that we could do with problem number 1. Use a linear approximation to estimate square root of 4.2 without a calculator, but you're not told what the function is. That's not so clear, perhaps. Then answer the question, is your estimate too big, an overestimate, or too small? That's supposed to be a TOO, too small, an underestimate, and why? What in the world? How can we do this if we don't know what the function is? You actually could have different choices for the function. Different choices could work. Now, perhaps the simplest choice is to use f of x equals, well, think about what we're doing here, taking the square root of something. How about just square root of x? Will that be good enough? Yes, it will be good enough as long as you pick a correctly and don't pick it to be 0. Now, a equals 0 is the most common thing to use for linear approximations. But if you're going to do that, it would produce a bad approximation. In fact, the derivative of this function at 0 is undefined. It's infinite, you might say. It would be a very, very bad approximation. Now, I could use a different function, like square root of x plus 4, all under the square root, and get a linear approximation to that near 0, and that could be useful. But I also could use this with a equal to 4. So that's what we'll do. This is x to the 1/2 power. Its derivative is therefore f prime of x 1/2 x to the negative 1/2 power, which is 1 over 2 square root of x. And because I picked a to be 4, close to 4.2 for one thing, that's a nice number in terms of its square root. Now, if I made this problem harder, I could make it harder by like doing square root of 5.2. Then would you want to use a equals 5? Well, then you'd have to estimate ultimately square root of 5. Without a calculator, that doesn't seem possible. So, I mean, you can do it, but it's not as good. So I've constructed this problem, so it's not going to be too bad to use that. F of a is f of 4, is square root of 4 is 2, and f prime of a is f prime of 4 is 1 over 2 square root of 4. Square root of 4 is 2. That'll be 1/4 or 0.25 to help me do it without a calculator. So, square root of 4.2, well, okay, let's write the L of x here. This implies L of x is 2 plus 0.25 times, in parentheses, x minus 4. That's the linear approximation, tangent line approximation. This is f of 4.2, which is well approximated, we hope, by L of 4.2. Plug in 4.2 into here, get 2 plus 0.25 times 4.2 minus 4. That's 0.2. This is going to be 2 plus 0.25 times 0.1 would be 0.025. Double that to get times 0.2, 0.05. 2.05 is our approximation for the square root of 4.2. Is it going to be too big or too small? We're using a tangent line to approximate a curve. Here's the square root function. Here's 4, say. We know square root of 4 is 2. We're trying to estimate square root of 4.2. We're not using the actual function. We're using the tangent line approximation, which is above the curve. The actual square root of 4.2 is the second coordinate of that point. We just approximated the second coordinate of this point right there to be 2.05. Well, actually, the exact second coordinate of that point is on that tangent line there is 2.05. It's going to be an overestimate. Too big. Yes, too big means TOO. Too big. Because the tangent line is above the curve, because the curve is concave down. That's why. If we want to confirm it with the calculator, 4.2 to the 0.5 power is the same as square root of 4.2. We should get a number a little less than 2.05. And we do, 2.04939. Okay, it's a pretty good approximation. This problem doesn't ask about error, but I am soon going to consider problems about error. In fact, the next problem. The error in the approximation is always the actual value minus the approximate value. Since our overestimate is too big, the actual value minus the approximate value is going to be negative. The error is going to be negative. That is allowed, and that it's good to keep track of sometimes. What is it approximately? What's the approximate error? Subtract the actual value, or excuse me, the approximate value from this. We get a negative number, about negative point, well, this is scientific notation here. This would be negative 6.0985 times 10 to the negative 4, which is approximately without scientific notation, negative 0.0006098, say. Let's round it to that, okay? So that's the error itself. Negative ultimately means our estimate is too big. It's a little confusing that way. Can also talk about the magnitude of the error, or absolute value of the error, and that is just this thing without the negative sign. Okay? Error is going to come up in the next problem. And this next problem deals with the function cube root of 1 plus x. For x near 0, so that means a is 0, confirm that local linearization, tangent line approximation, says that this function is approximately 1 plus 1/3 x. And then b, by using a graph, we're going to estimate the magnitude of the error. Okay? So let's do part A first. The function is cube root of 1 plus x, same as 1 plus x quantity to the 1/3 power. And by the way, that's definitely not the same as 1 to the 1/3 plus x to the 1/3. That's definitely very, very wrong to write that. This actually expands as what's called an infinite series. You can look it up. It's called the binomial series. Infinite series means that's sum of terms going on forever. We're going to need to find its derivative. Bring down the 1/3, 1 plus x to the negative 2/3. Chain rule would mean also multiply times the derivative of 1 plus x, but that's just times 1, so it doesn't change it. The a is 0. We're for x near 0, that means a is 0. F of 0 is 1 to the 1/3, which is the cube root of 1, which is 1. And f prime of 0 is 1/3 times 1 to the negative 2/3. That's the same as 1 over 1 to the positive 2/3, and anything to the 2/3 power, you can square it first, then take the cube root. Anyway, because it's 1, we still get 1. 1/3 times 1 is 1/3, and that confirms it. Therefore, L of x is 1 plus 1/3 times x minus 0 is 1 plus 1/3 x. So the cube root of 1 plus x is approximately 1 plus 1/3 x for x close to a, where a is 0, for x approximately equal to 0. This is a nice way to approximate that kind of cube root. So we could use it to approximate cube roots of numbers close to 1. Part B, again, using a graph. We'll use technology here. Decide if the approximation is over estimate or an underestimate, and estimate to 1 decimal, place the magnitude of the error in absolute value for x between negative 1/2 and positive 1/2. So let's use the technology here. So I will graph the cube root of 1 plus x. I'll type it in here as 1 plus x all to the 1/3 power. And then we'll also graph the linear approximation, 1 plus 1/3 x. I'll type it in as 1 plus x over 3. Near 0, let's go ahead and graph it on this window here initially. X goes between negative 1 and 1, same for y. So here's the cube root of 1 plus x. I better pick a different window here. I should have realized that. Let's go back and pick a different window. You can see the tangent line approximation there. Let's pick a different window for y especially. So here's a decent window. And then our tangent line approximation, you can see the graph is concave down just like the square root function was. So the linear approximation is above it. It's going to give overestimates with negative errors. It's an overestimate. Technically, the errors themselves are negative. However, we're after the magnitude of the error. So we take the absolute value of that. And we're estimating it to 1 decimal place. Now, it's over an entire interval. The error itself and the magnitude of the error will change depending on what x is. We're trying to find where is the error biggest in absolute value. Let's go back to the calculator and change the window here. Let's go negative 1/2 to positive 1/2 for x. Negative 0.5 to positive 0.5. Oh, it probably would be good to zoom in closer to y equals 1 as well. Let's try going from let's try 1.7 maybe to 2.3. Let's just give that a try and see how we do. And let's make the scale in the y direction smaller. How about 0.05? So we're going to remember that 1.7 to 2.3 with tick marks 0.05 apart. Let's see how it looks. Graph it. I'm not sure what's going on. It seems to be stalled. Sorry about that. I realized I picked a really bad window. I want y near 1, not near 2. 0.7 to 1.3. Here we go. Now we can see it. Okay, so this is the cube root function, cube root of 1 plus x. And we have its tangent line approximation. What we want to do is we want to think about where are these curves farthest apart. It looks pretty clear it's on the left when x is negative 0.5. And how far apart are they? We can estimate it by tracing here. Trace. On the curve itself, when x is negative 0.5, I guess I could plug in negative 0.5, couldn't I? Y is about 0.7937. And on the linear approximation, it's 0.83 repeating. 0.7937. Let's take the absolute value of 0.7937. Just confirm that. Yeah, I'll just round it to that. Minus 0.8333. That's where the magnitude of the error is biggest. You can see the curves are farthest apart over this interval. So that'll be an upper bound for the error over the entire interval, the magnitude of the error. And what is it? I can do the subtraction in the opposite direction. It's about 0.0396. So the error over the entire interval is definitely less than 0.04 for all x between negative 1/2 and positive 1/2. The magnitude of the error is less than 0.04. Number 4 is an equation solving application of local linearization. We've got this equation, x plus natural log of 1 plus x equals 0.2. And we're saying it has a solution, this equation, for x that you can solve for near x equals 0. You can't solve for it symbolically. It's a function here that cannot be solved for x explicitly in terms of what's over there, because it's a combination, a sum of an x term and a log of something. You can try exponentiation and so forth. It's not going to be helpful. We have to approximate the solution. Let's just confirm that this really does seem right, that there is a solution near 0. So I'm going to graph, make different graphs this time. The function x plus ln of 1 plus x. And I'll also graph a horizontal line at 0.2, graphing it near 0. And the output here, yeah, we want an output close to 0. So let's go from, say, negative 0.5 to positive 0.5. So here's the function itself. It looks like it goes to the origin, and in fact it does. If you plug in 0 there, you get 0. It looks pretty straight, but it's actually a curve. It is slightly curved. And there's the horizontal line at 0.2. You can see the intersection point there is close to 0.1. We could try to calculate it. First curve, second curve, and guess. Looks like the intersection point is close to 0.10246. Okay, 0.10246 is a more precise approximation to where they intersect, but we want to use local linearization, replace the left-hand side with its linearization evidently near 0, that's the A, and find an approximate value for the solution. It's going to be close to 0.1. So here f of x, well, okay, let me just focus on the ln part, ln of 1 plus x. I could do the entire thing as well. It's not a big deal. That's the one part that I'm going to focus on for linearization. Okay, let's go ahead and do the whole thing just to illustrate that we can. So there's the whole thing. What is its derivative? It's going to be 1 over 1 plus x plus 1. We're plugging in a equals 0. Here we get ln of 1 plus 0 is 0 plus 0 is 0. And f prime of 0 is 1 over 1 plus 0 plus 1. 1 plus 1 is 2. Therefore, L of x, the linearization, is 0 plus 2 times x minus 0, just 2x. We're replacing the left-hand side of the equation with its linearization. Do that now. 2x equals 0.2, a very simple equation. Has solution, exact solution, 0.2 over 2 is 0.1. And that exact solution for this simple equation is our approximate solution for this equation. And we did see in the calculator that a more precise answer was a bit bigger than 0.1. But this was pretty close. Number 5 is a word problem that as you look it over, it looks really, really hard. It's not quite as hard as it looks, but it is still a little tricky. Let g be the acceleration due to gravity. The period t of a pendulum. What's a pendulum? It's a mass on a bob swinging back and forth. And so the period is how long does it take to go back and forth as it swings. That's what a pendulum is. Its length L, that's how long the rod connecting the bob is given by this equation. The period is 2 pi times the square root of L over g. Yes, this is a cursive L here, if you're wondering. It's not an E or anything. L is the length of the pendulum, and g is the acceleration due to gravity near the surface of the Earth. Part A, show that if the length of the pendulum changes by a small amount, delta L, in other words, if you get a slightly different pendulum, then the change in the period is given by this. Change in the period is approximately the previous period of the previous pendulum divided by 2 times L, where L is the length of the previous pendulum, times the change in the length based on the fact that now we're using a new pendulum where the rod has a slightly larger length, for example. Okay, so that seems difficult. What's the main idea? The main idea is that the change in the period, t represents the period, is approximated by, for small changes in the length of the pendulum, the rate of change, the derivative of t with respect to changes in the length, dt dl in Leibniz notation. I'm actually going to use, instead of an ordinary looking d, I'm going to use a funny looking d, you could call it a d, that looks like this. This is going to emphasize that I could think of this as what's called a partial derivative. And the reason I'm doing this is that this expression could be thought of as a function of 2 variables, L and G. And I want to sort of highlight that by using fancy curvy looking D's instead of ordinary looking D's. Now, could I use ordinary looking D's? Sure, I could, okay? But I'm going to use this to emphasize that that's traditional to use partial derivative notation when you've got 2 variables there. Now, you might be wondering, well, the acceleration due to gravity is not a variable, it's a constant. Actually, it is a variable, as I'll talk about as we go through the problem here. But anyway, the change in period is approximately the rate of change of the period with respect to the length times the change in the length. This is an L here. Okay, so I guess I have to find that derivative. Are partial derivatives found differently than ordinary derivatives? No, they are found just like ordinary derivatives, although you got to, in your mind, pretend the other variable, so to speak, is actually a constant. It's going to be more convenient to write this as 2 pi times L to the positive 1/2 times G to the negative 1/2. That is okay to do. I'll let you think about that. And so the partial derivative of the period with respect to L treats the G as if it's constant. So it just stays there. It's a multiplicative constant. It just stays there. The only thing I have to differentiate is the L to the 1/2. The 2 pi stays there. 2 pi times, bring down the 1/2, subtract 1 from the exponent, and get this. It can be simplified a little bit. The 2's divide out. We could write this as pi L to the negative 1/2, G to the negative 1/2. We could combine that. We could also write it as pi over square root of L times G. Okay? That is the derivative, and that can get plugged in here. But, something kind of weird happens here. I'm going to plug it in with exponents. It doesn't look like the answer, does it? Doesn't look like that. Looks like that. It's different. Doesn't even have any t's in it. Don't panic. It's okay. This is how delta t simplifies in terms of little l, little g, and delta L. How does the right-hand side of this simplify? Well, you might look at it and say, well, it doesn't really simplify. Yes, it does. Replace t with this and see what happens. So make that replacement. 2 pi L to the 1/2 g to the negative 1/2 over 2L times delta L. We do get some simplification. The 2's divide out. The L to the 1/2 divided by L is the same as L to the negative 1/2. I could subtract the exponents. And indeed, I get the exact same thing as this. I get pi L to the negative 1/2 g to the negative 1/2 times delta L. So those match, making me happy. And that means we have verified part A. Okay? So a lot of symbol pushing here. It does have meaning, and we can give it some meaning here based on part B. If the length of the pendulum increases by 2%, a small change, by what percent does the period change? This still seems kind of tricky. How in the world can we do this? We want to use part A. I mean, that's typical in these kinds of problems. If you've got a part A and you're going to go into part B, sometimes you are going to want to use part A. I'm going to take part A and rewrite it. I'm going to divide both sides by t. Delta t over t is approximately 1 over 2L times L, which I'll write as 1/2 times L over, or excuse me, delta L. That's a delta L over L. Now, think about percentages. If you got money in the bank account, like $100, say, and you earn some interest, like $2 over the course of the year, your money went from 100 to 102. That's a 2% increase. The change in the amount of money was 2. If you divide by the starting amount, 100, 2 divided by 100 is 2%, 0.02. We have similar kinds of expressions with these fractions here and here. A change in an amount divided by the starting amount. Change in the period divided by the original period. Change in the length divided by the original length. We are, again, we've got a pendulum that's got a certain period. We change it to a new pendulum with the same mass. It's a little longer, a line that's a little longer. That's how you want to think about this. It's a 2% increase in part B. In other words, it's 0.02. And this is supposed to represent the change, the percent change in the period. 0.01 or 1%. That's the answer. Okay, so the approximate change in the period as a percent is 1%. It is an approximation because it's based on a linear approximation. Okay, this is a nonlinear function of both L and G. We are getting a linear approximation here. That could be useful information. The 1%, there's nothing special about the change in 2%. It could be 1%. It could be 1.4%. You do want to keep it small because it's good when these approximations are good when you have small changes. The percent change in the period is always 1/2 the percent change in the length of the pendulum. That could be useful information to think about as you are doing experiments in science. Part B. Oops, sorry. This is part C, actually. Part C, and this is going to be part D. Part C. Dangers of copy and paste, to tell you the truth with that. Show that if the acceleration due to gravity changes by a small amount, delta G. How could that be? Didn't your physics teacher say the acceleration due to gravity is constant? It's not really constant, actually. That's just an approximation. You might call it a 0th order approximation. If you go up high into the sky, at the top of a mountain, in an airplane, even higher, the acceleration due to gravity actually gets smaller because you're getting further away from the center of the Earth. So it's not constant. We can think about changing it by, like, for example, climbing or falling in elevation, going up or down a mountain. We want to show that this approximate equation is true. It's very similar to the original part A and B. But now I'm taking the derivative with respect to G instead of with respect to L. I'm using partial derivative notation again. I want to differentiate this now with respect to G, treat everything else here as a constant, bring down the negative 1/2, 2 pi L to the positive 1/2, or positive 1/2 times negative 1/2 G to the negative 3/2 times delta G here in this expression. Yikes. It does simplify a little bit. The 2's divide out again. I get negative, I I could write it as square root of L over G times square root of G times delta G. That's one way to write that. It doesn't look like this, but do the same thing we did previously. The right-hand side is negative T over 2G times delta G. Replace T with this. Get negative 2 pi L to the 1/2 G to the negative 1/2. Divide by 2G times delta G. And the 2's divide out again. This does simplify to negative pi. Let's see here. We will have an L to the 1/2 in the top. We could subtract the exponents here. Negative 1/2 minus 1 is G to the negative 3/2, which means it also could go in the bottom as G times square root of G times delta G. We again get the same thing. That makes us happy here. We have confirmed part C. And now for part D, do something similar as the original part B. If the acceleration due to gravity increases by 2%, for example, by going down a mountain, by what percent does the period change? Do the same kind of thing. Take the approximate equality between this and divide both sides by T. Delta T over T is approximately negative 1/2 times delta G over G. So negative 1/2 times, now G is increasing by 2% by going down the mountain. This becomes negative 0.01 or negative 1%. In other words, the relative rate of change of the period is negative 1%. It goes down. When the period goes up, as it did in part B, because the pendulum got longer, that means a slower motion. It's going back and forth a little slower when the pendulum is longer. When G increases by going down a mountain to, say, sea level, delta G over G is positive. The change in period is negative. That means the period is getting smaller. That means it's a faster motion. That's good to think about. Our final problem is kind of theoretical, thinking about errors as functions. Let f of x equal x to the 4th and let a equal 1. Part A says find a formula for the error e of x in the tangent line approximation to f of x near x equals a. You remember that problem where we were thinking about errors graphically and we said that it depends on x. The error is different for different values of x. That's what's going on here, and we want to actually find a formula for the error. All right, well, we need the tangent line approximation first. F of x is x to the 4th. F prime of x is 4x cubed. A is 1. F of 1 is 1 to the 4th is 1. And f prime of 1 is 4 times 1 cubed, which is 4. So L of x is f of 1 plus f prime of 1 times x minus a, which is x minus 1. That is L of x as we would most typically use it to approximate f of x near x equals a, which is 1. I will expand it for the purposes of doing part A here. So this is 1 plus 4x minus 4. That'll be 4x minus 3. That's the L of x function in expanded form, slope-intercept form you might call it. What's e of x then, the error function? Well, again, as I said in the previous problem, not the exact previous, but a few problems ago, this is actual value minus approximate value. I forgot to mention that it's very fortunate that this goes in alphabetical order here. Actual comes before approximate. That helps you remember it. The actual value is f of x, the function itself. The approximate value is L of x. The function itself is x to the 4th. The approximation is 4x minus 3. Make sure to use parentheses like I'm doing before you simplify. The error function has a formula that simplifies to x to the 4th minus 4x plus 3. That is e of x here. Okay, big deal. Well, we could graph it. And in fact, that's what we're going to do in part B. Graphically confirm that the error function divided by x minus a is approximately 6 times x minus a near x equals a. Again, a is 1 here. And you might be wondering, why in the world would we care about doing such a thing? Before I actually do it, let's just talk about why it's important. Errors in linear approximations of differentiable functions are such that they go to 0 really fast as x approaches a. Certainly there's the error function for this linear approximation at a equals 1. Certainly the value of this function is 0 when x is 1. 1 to the fourth minus 4 times 1 plus 3 is 1 minus 4 is negative 3 plus 3 is 0. But I claim even more. I claim this goes to 0 very rapidly as x goes to 1. In fact, so rapidly that when you divide it by x minus 1, which is also going to 0 as x approaches 1, you get something that goes to 0 as x approaches 1. That was a mouthful here. E of x goes to 0 so fast as x approaches a, which is 1, that if you divide it by x minus 1, which also goes to 0 as x approaches 1, the whole expression still goes to 0 as x approaches 1. And it happens to be the case here that the coefficient there is 6. We're going to graphically confirm this, so I won't actually write anything down. We'll just use the calculator. Get rid of this previous example. OK, so I'm going to graph both sides of this approximate equation. E of x divided by x minus 1, as I need parentheses here. Actually, it turns out, I'm not going to actually do this, that this function x to the fourth minus 4x plus 3 is actually divisible by x minus 1. If you did a long division of polynomials, you would get a 0 for the remainder. And so you could actually simplify this division to being actually a cubic when x is not equal to 1, so that you're avoiding the place where this is undefined. But we're not going to do that. Let's also graph 6 times, in parentheses, x minus 1. These graphs should be very close together when x is close to 1. And in fact, effectively, this should be the tangent line approximation to the other one, although the other one has a removable discontinuity at x equals 1, technically speaking, but we could fill in the hole. We're graphing this near 1. Let's go from 0 to 2 here. And the output near x equals 1 is 0, actually. So let's go from negative 1 to 1. So here is this thing that is, the calculator knows there should be a gap near 1 there, actually. And it did graph the line. You can barely see, OK, it filled that in because it would also graph the line there 6 times in parentheses x minus 1. You can see they're virtually indistinguishable from each other. Let's make the y range go a little further here. Maybe negative 3 to 3 instead, to perhaps see that they are not the exact same functions better. So there's the original function. Technically, it's got a hole in the graph when x equals 1. If you fill in the hole, because it's a removable discontinuity, you would actually get a continuous and differentiable function there, and this line would be the tangent line there. So we have visually, graphically confirmed this approximate equation here. In part C, we're showing that the 6 actually turns out to be the second derivative of this function at a, which is 1, divided by 2. You might wonder where that comes from as well. It's the theoretical thing. And graphically confirm this theoretical fact that will be true for twice differentiable functions near a. The error will be approximately a quadratic in x minus a. And that definitely goes to 0 as x approaches a, in fact, pretty rapidly because it's being squared. So we're just going to do 2 things here. We'll confirm that f double prime of a over 2 is 6, and we'll graphically confirm this approximation. So f double prime of x, second derivative, I need to differentiate this, is 12x squared. So f double prime of a, which is 1 over 2, is 12 times 1 squared over 2. 12 over 2 is 6. There's our 6. Yep, confirming that fact right there. And yeah, let's now graphically confirm the error is approximated by that quadratic function, which jives, is consistent with part B, actually. Effectively just multiply both sides by x minus a. But we'll look at the graphs as well, and that'll be the last thing we do here. So let's just clear that out. Do x to the fourth minus 4x plus 3 again, but now we're not going to divide by anything. And with this second function, we're just going to square that. And these functions are going to be close together near 1 as well. Let's just see what it looks like on this window. So there's the error function. And next is its quadratic approximation. You can see it's pretty good. Thanks for watching.